So there is this caricature that just kind of lives in the public consciousness when you say the word mathematician. You immediately picture, I don't know, a dusty chalkboard somewhere.
Yeah, with someone with wild hair just hunched over in a basement.
Exactly. Just hunched over, multiplying these massive numbers together. Like, quick, what is 5,423 times 9,000?
Right, the human calculator trope.
Yeah.
As if the entire job description is just being a slightly slower and way more expensive Excel spreadsheet.
I mean, I think a lot of us carry that trauma from grade school. We really do think math is just memorizing times tables and following these rigid steps.
Yeah.
But we are taking a deep dive into Brendan W. Sullivan's work today. It's called Everything You Always Wanted to Know About Mathematics. And if there is one massive takeaway right off the bat, it's that this image is not just a little off, it is fundamentally wrong.
Oh, it couldn't be further from the truth. In fact, Sullivan makes a really strong point that most professional mathematicians are actually terrible at doing arithmetic in their heads. Yeah, they make change at the grocery store and get it wrong all the time. They aren't calculators at all. They are architects of logic.
Which honestly makes me feel a lot better about my own tipping math at restaurants. But if they aren't crunching numbers all day, what are they actually doing?
They are hunting for truth. Real math is closer to philosophy, or even art, I would say. It's a highly creative discipline. It's about devising statements, hypotheses essentially, and then finding a way to prove beyond a shadow of a doubt that those statements are true.
Right.
And not just true on Tuesdays or true most of the time, but true always and forever.
That always and forever part is really the kicker here. It's a level of certainty that you just don't get in other fields. Like in psychology or economics, you get correlations right. In math, you get absolute certainties.
Precisely. Think about physics for a second. If you drop a ball 1,000,000 times and it falls every single time, you have a very strong theory of gravity. But strictly speaking, you haven't proven it will fall the millionth and first time.
Because maybe the laws of physics change on the weekend.
Right, exactly. But in math, checking 1,000,000 times is essentially worthless. You need a logical argument that guarantees the result across the entire universe of numbers.
So that is our mission for this deep dive. We are going to strip away the jargon and all those scary formulas that made us sweat in high school. We are going to look at what it actually means to think mathematically.
Yeah.
We're going to look at the logic, the puzzles, and those really satisfying aha moments that define the field.
We're basically going to learn the art of truth today.
And to get there, we really have to start with the concept of a proof. Because in daily life, proof usually means I saw it happen or here is a screenshot of the text message. That's evidence. But Sullivan is very clear that in math, evidence is not proof.
Not at all. To illustrate the difference, I want you to join me in a quick thought experiment. Imagine you are the very first human to make contact with an alien civilization.
Okay, high stakes. I'm ready.
Very high stakes. Now, this alien is highly intelligent, but they have never seen an Earth geometry textbook. They've never heard of Euclid or Pythagoras. How would you convince this alien? Absolutely convince them that the angles of a triangle always add up to 180 degrees.
Oh, man.
Or, to use the classic example, how would you convince them that the Pythagorean theorem is actually true?
Okay, let's stick with Pythagoras. A squared plus b squared equals c squared. The leg squared plus the other leg squared equals the hypotenuse squared. My instinct, I draw a right triangle on a piece of paper, I take out a ruler, I measure the sides, I do the math, and I show the alien the calculator and say, look, it works.
And the alien just looks at you totally unimpressed. They
Yeah.
say, okay, you've shown me it works for this specific triangle you drew with your clumsy human hands.
Yeah.
But what about a triangle the size of a galaxy?
Right.
What about a microscopic triangle? What about the one you haven't drawn yet?
You really think the alien is going to be that pedantic?
If they think mathematically, yes, absolutely. Because measurement has error. Maybe your ruler is slightly off. Maybe the pencil line is just a bit too thick. You haven't proven the theorem is true for all triangles. You've just shown it's roughly true for one.
Okay, that makes sense.
To really prove it, you need a logical argument that covers every possible triangle that could ever exist.
And Sullivan actually walks us through 4 attempts to do exactly this in the source material. What's fascinating is that some of these look like amazing proofs, but are total garbage, and some look almost too simple, but are profound. Let's break these down, because spotting a fake proof feels just as useful as understanding a real one.
I completely agree. Let's do it.
The first method Sullivan highlights is called the square within a square. This one felt remarkably visual to me. Like, I didn't need a calculator to get it, but I did have to close my eyes and visualize it.
It is very visual, but it's backed by rigorous algebra. This is what mathematicians call a constructive proof.
Mhm.
I want everyone listening to visualize this with us. Imagine a large square. Let's say the side of the square is length a plus b. So it's a big square.
Okay, I've got a big square in my head, like a giant floor tile.
And then inside that square, you place 4 copies of your right triangle. You arrange them right in the corners. If you do it perfectly, the hypotenuse of those triangles, the long C sides, they form a smaller, tilted square in the very center.
I can picture that. It looks like a diamond sitting inside a box.
Exactly. Now, we don't need to measure a single thing. We just talk about the area. We can calculate the area of the big box in 2 totally different ways.
Mm-hmm.
First, just the standard way. Side times side. That's a plus b squared.
Simple enough. Length times width.
But the area is also the sum of all the pieces inside, meaning the 4 triangles plus that diamond square in the middle, which has an area of c squared.
So you basically have 2 different descriptions for the exact same amount of physical space.
Right. And in math, if 2 things describe the exact same value, they must be equal. So you set those equations equal to each other. A plus b squared equals the area of the individual pieces.
Yeah.
And then you just simplify. You do a little basic algebra, and the extra terms just cancel out.
And you are miraculously left with a squared plus b squared equals c squared.
Boom. That is a valid proof. It's logical, and it relies on basic area rules that we already agreed on. There is no way for the alien to argue with it. It doesn't matter if the triangle is the size of the universe. The algebra holds up perfectly.
Okay, so that's the gold standard. It feels sturdy. But then Sullivan shows us this other proof, and honestly, it looked way more professional to me. It had a diagram labeled triangle ABC, and it had these dotted lines for altitudes. It was talking about ratios and similar triangles. It really looked like something that would get you an A+ in high school geometry.
It certainly looks the part. This is the similar triangles attempt.
Mm.
It sets up these complex ratios between the sides and does a bunch of algebra to derive the theorem. But there is a fatal flaw hidden deep inside it, a complete poison pill.
And that flaw is...
Circular reasoning.
Ah, the classic logic trap. Explain how that works here.
Well, to make that proof work, you have to use the mathematical property of similar triangles. You have to be able to say, because these angles are the same, the ratio of the sides must be x. But in this specific geometric setup, the only reason we know those triangles are similar in the first place is because we are implicitly assuming the Pythagorean theorem is true.
Wait, so to prove the theorem, you are using tools that only function if the theorem is already a proven fact.
Exactly. It's called begging the question. It's like applying for a bank loan and saying, well, you can trust me to pay you back. The bank asks why. You say, because I'm trustworthy. They ask who says. And you say, well, I do.
It's a completely closed loop. You can't use the definition of a word to define the word itself.
Right. You might actually be trustworthy, but as an argument, it's completely worthless.
Yeah.
And this is the danger of math that looks fancy. You can hide really bad logic behind very complex diagrams.
That is sneaky, because if you aren't paying close attention to the underlying assumptions, the math itself, like the calculation part, is actually correct.
The arithmetic is perfect, but the logic is broken. And in mathematics, logic is king.
Then there were the other 2 proofs, which were, well, let's just call them human proofs. One was literally just a drawing of a circle and a triangle with absolutely no text, just a bold caption that said, "Behold."
The visual proof. I actually love these for intuition. They give you that quick spark of understanding. But they fail completely as rigorous proofs. A proof is fundamentally an act of communication. If I just show you a picture, you might see the pattern, or you might focus on the entirely wrong thing. If I can't explain why it works using shared rules, I haven't proved anything to you. I've basically just shown you a magic trick.
And the last one was the authority argument.
Right, the old, it must be true, otherwise my teachers have been lying to me for 12 years.
I mean, socially speaking, that's a pretty safe bet. We built bridges and airplanes based on this stuff. If it was wrong, things would be falling out of the sky.
True. Pragmatically it works. But mathematically it's garbage. In math, there are no authority figures. It doesn't matter if Isaac Newton himself floats down from the heavens and hands you an equation. If the logic doesn't track, it's wrong. That is sort of the democratization of math. A high school student can prove a Nobel Prize winner wrong if they find a flaw in the logic.
So a valid proof needs to be logically sound with no circular reasoning, and it needs to be clearly communicated. No trust me bro allowed.
Exactly. And this brings us to the core idea that math is actually a language. It has symbols and rules, just like English has grammar and syntax.
But the stakes feel a lot higher in math. Like if I make a grammar mistake right now, you probably still know what I mean. I can dangle a participle and nobody gets hurt.
Right, natural language is very forgiving. It relies heavily on context. But in math, A small grammar mistake can literally break the universe.
Sullivan gives this incredible example of a proof that seemingly demonstrates that 1 equals 2.
It's a classic party trick.
And looking at it, the algebra seems totally fine. You start with x equals y. Then you multiply both sides by x. Then you subtract y squared. You do some factoring. And eventually you divide both sides by x minus y, and you're suddenly left with 2 equals 1.
It looks perfect to the untrained eye.
Yeah.
It follows all the standard algebraic manipulations we learned in school.
Yeah.
But did you catch the trap?
I think I did, but honestly, only because Sullivan pointed it out. It happened right at that division step.
Right. Go back to the very first thing we established. X equals y. If x and y are the exact same number, what is x minus y?
0.
And at the very end of the proof, we divided both sides by x minus y.
They divided by 0.
Which is the mathematical equivalent of setting off a nuclear bomb. In the language of mathematics, division by 0 is undefined. It's nonsense. It completely destroys the logical framework. Once you divide by 0, you can literally prove anything. You can prove 1 equals 2. You can prove black is white. You can prove I am the king of England.
So the strict rules exist to keep the entire system from just collapsing on itself.
The precision really matters. There was another great example in the text where someone proves that 0 equals 36.
Oh, right. That one messed with my head for a second.
That one is a stern warning about square roots. We tend to be a bit lazy. We think if x squared equals 25, then x must naturally be 5.
But it could just as easily be -5, because -5 times -5 is also 25.
Exactly. That fake proof relies entirely on ignoring the negative root. It confuses the direction of implication.
Yeah.
Just because if A then B is true, it doesn't automatically mean if B then A is true.
It really is all about being rigorous. But sometimes logic isn't just about spotting errors in algebra symbols. It's about spotting errors in how we tell stories.
Yes, logic is the ultimate defense against bad narratives.
This perfectly brings us to the funny money riddle. I remember hearing this as a kid at summer camp and being totally baffled. I lay awake at night thinking about where the missing dollar went.
It's a fantastic example of an emotional trap versus a logical reality.
For everyone listening, let me set the scene. You have to follow the money closely here. 3 friends check into a hotel room. The clerk charges them $30, so they each reach into their pockets and pay $10. 10, 10, and 10.
Simple enough. $30 is in the till.
Later, the clerk realizes he made a mistake. The room should have only been $25, so he takes 5 $1 bills from the register and gives them to the bellhop to return to the guests.
Okay, so the money is moving back to the friends.
But the bellhop is a bit shady. He thinks, well, I can't split $5 among 3 people evenly, so he just pockets $2 for himself as a tip and gives $1 back to each friend.
So everyone gets $1 back.
Right. Now here's the math that breaks your brain. Each friend paid $10 originally and got $1 back. So effectively they paid $9 each.
Correct.
9 times 3 friends is 27. The bellhop kept $2 in his pocket. 27 plus the bellhop's 2 is 29.
And they started with 30.
Where did the missing dollar go?
Where is the missing dollar? That question is basically weaponized confusion.
It works so well. Even though I know the answer, I feel like I lost a physical dollar just saying it out loud.
The trap here is that the narrative forces you to perform a calculation that has absolutely no meaning. You're adding 2 numbers that have no business being added together.
Walk me through that. What do you mean?
Look at the equation the riddle proposes. 27, which is what the friends paid, plus 2, which is what the bellhop kept. Why on earth are we adding those? The bellhop's tip is already a part of the $27 the friends paid.
Oh, wait. Let me think about that. They paid $27 total.
Right. Out of that $27 that left their wallets, 25 went to the hotel and 2 went to the bellhop. 25 plus 2 is 27. All the money is perfectly accounted for.
So the 30 doesn't even matter anymore.
The 30 is ancient history. 3 of it went back to the friends. You can't add the bellhop's tip to the friends' payment because the tip came from the friends' payment.
Yeah.
You're just double counting.
Sullivan mentions that if you change the numbers, like make them really big or really messy, the illusion vanishes instantly.
Right. If the discrepancy was $500, or if the math was just ugly, you wouldn't be looking for a missing amount. You'd instantly realize the equation paid plus tip equals original is total nonsense. The number 1 is just small enough to make us think it's a rounding error or a magic trick.
So logic actively protects us from bad storytelling. But math isn't just about checking work or debunking riddles. It's also incredibly creative.
This is my absolute favorite part of the text. we have to talk about Carl Friedrich Gauss.
The prince of mathematicians himself.
And this specific story takes place when he was just a child in elementary school, back in the late 1700s.
The story goes that his teacher was tired, maybe hungover, who knows. He wanted to keep the class busy so he could take a nap. So he told them to sum up all the numbers from 1 to 100, 1 plus 2 plus 3, all the way up to 100. He figured it would take them an hour of tedious addition.
And young Gauss, maybe 10 years old, walks up to the desk seconds later and just slaps down his slate. There it is. The answer is completely correct.
How did he do it? I mean, he didn't have a calculator. He couldn't have added them that fast.
He didn't add them linearly. That's the brute force way. Gauss saw a structure that no one else in the room saw. He realized that if you take the first number, which is 1, and the last number, which is 100, they add up to 101.
Okay.
Then you take the second number, 2, and the second to last number, 99. What do they add up to?
101.
And 3 plus 98.
101. I see where this is going.
Exactly. He realized the entire list is just pairs of numbers that equal 101. Since there are 100 numbers in the list, there must be exactly 50 pairs. So the math isn't 1 plus 2 plus 3. It's just 50 times 101.
Which is 5,050.
Done. Instantly. That is true mathematical thinking. It's not about doing the hard work. It's about finding the clever path that makes the work easy. It's about pure pattern recognition.
And this actually leads to a general formula, right? N times n plus 1 divided by 2.
Yes. But what I really love is how Sullivan extends this visual thinking to other types of sums. Like, what if you want to add up just the odd numbers? 1 plus 3 plus 5 plus 7.
Sullivan describes this really cool visual of corners or L shapes for that.
This is beautiful. I want you to close your eyes for a second. Imagine a single square block sitting on a table. That's the number 1.
Got it. 1 block.
Now take 3 more blocks, arrange them in an L shape, and wrap them around the top right corner of your very first block. What shape do you have now?
I have a bigger square. It's 2 blocks by 2 blocks.
Right. So 1 plus 3 equals 4, which is 2 squared. Now take the next odd number, which is 5. Take 5 blocks, make a bigger L shape, and wrap it around the corner again.
Now I have a 3 by 3 square.
So 1 plus 3 plus 5 equals 9, which is 3 squared.
Wait, so adding odd numbers in sequence always gives you a perfect square?
Always. The sum of the first n odd integers is exactly n squared. And you can prove it just by mentally stacking blocks in a corner. It turns a boring arithmetic problem into a beautiful geometric certainty.
It really connects things that feel totally separate. Like arithmetic is just counting, but geometry is shapes. Seeing them locked together perfectly like that is incredibly satisfying.
It's the interconnectivity of truth.
Speaking of deep truths, let's pivot and talk about the infinite. We've been dealing with finite numbers so far, but the deep dive gets really wild when we look at prime numbers.
Primes. The absolute building blocks of arithmetic. Numbers divisible only by 1 and themselves. 2, 3, 5, 7, 11.
Right. And the big question is, do they ever stop? Because as numbers get bigger, they have way more factors, so primes should theoretically become rarer. Is there a final, last prime number?
This is one of the oldest proofs in the book. It goes all the way back to Euclid over 2,000 years ago, and it uses a brilliant technique called proof by contradiction.
How does that work in practice?
It's basically a legal trap. You start by assuming the exact opposite of what you actually want to prove. You say, okay, let's pretend for a moment that there is a final prime number. Let's say there are only a finite number of primes in the universe, and we have them all written down on a list.
Okay, we have the complete list. No primes exist anywhere outside this piece of paper.
Now Euclid says, let's do a little math. Multiply all those numbers on your list together, and then just add 1. Call this huge new number n.
So n is the product of all existing primes plus 1.
Now we have to ask a simple question. Is n prime?
Well, if it is, we are in big trouble. Because n is way bigger than any of the numbers on our list. So we just found a new prime that wasn't on the complete list.
Correct. That would instantly contradict our assumption. But what if n is not prime? If it's composite, it must be divisible by some prime number.
Right, because that's how numbers work. Every number is built out of primes.
But check this out. It can't be divisible by any of the primes on your list.
Wait, why not?
Because if you divide n by any prime on your list, you will always get a remainder of 1. That's literally how we built the number. We multiplied them all together and then deliberately added 1 to the end.
Oh, right. It's like saying if I have 5 times something plus 1 and I divide it by 5, I'm always left with that extra 1 hanging over.
Exactly. So if n is composite, it must be divisible by a prime that is not on your list.
So either way, whether n turns out to be prime or composite, there is a prime number that exists outside our finite list.
Exactly. The very assumption that the list is finite leads directly to a logical contradiction. Therefore, the list cannot possibly be finite. The primes must go on forever.
That is just logical judo. You use the assumption entirely against itself.
It is so elegant. But there is one more proof from Sullivan that I think is even more mind-bending than the primes. It involves irrational numbers.
Irrational numbers are numbers you can't write as a simple fraction right, like pi or the square root of 2. They just go on forever without a repeating pattern.
Right. Now, here is the big question. Can you take an irrational number, raised to the power of another irrational number, and somehow get a rational number?
And irrational to the power of an irrational equals rational. My gut says no way. That seems way too messy. It feels like mixing two highly chaotic things should just create more chaos.
It feels like it should create a super irrational number. But the proof that the answer is actually yes is stunning because it's entirely non-constructive.
Break down that term for me, non-constructive.
It means we can prove the answer is yes without actually pointing to the specific numbers that do it. We can mathematically prove a solution exists without knowing what the solution actually is.
That sounds like actual magic. How is that possible?
Consider the number, the square root of 2. That is definitively irrational. Now consider the square root of 2 raised to the power of the square root of 2.
Okay, square root of 2 to the square root of 2.
Is that number, that whole expression, rational or irrational?
I have absolutely no idea.
Neither do I. And here's the absolute genius part. The proof doesn't care because logic gives us two distinct options. It's called the law of the excluded middle. It has to be one or the other. Okay, I'm with you. Case 1. If that number happens to be rational, then we're done. We found our example. An irrational to an irrational made irrational.
Okay, that's the easy path. But what if it's irrational?
Case 2.
Okay.
If that number is irrational, then let's just do one more step. Let's take that number square root of 2, the square root of 2, and raise it to the power of the square root of 2 again.
So you have the expression raised to the square root of 2.
Basic exponent rules say when you raise a power to a power, you just multiply the exponents. So what is the square root of 2 times the square root of 2?
That's just 2.
So the whole massive chaotic thing simplifies to the square root of 2 squared, which is
2, and 2 is definitely a rational number.
exactly. So if the first number was rational, we win. If the first number was irrational, the second calculation makes it rational, and we still win. We don't know which path is the right one, but we know 100% that one of them absolutely leads to the answer.
That is wild. We basically trapped the truth in a corner. We proved it exists without knowing exactly which numbers make it happen.
It perfectly showcases the power of pure logic. We didn't calculate it, we deduced it. And that, to me, is the true essence of this deep dive.
So if we zoom all the way out, what does this all mean for you listening? We've looked at alien triangles and infinite primes and young Gauss in his classroom.
I think the synthesis here is that math isn't actually about the numbers. It's about the relationships between the numbers. It's about spotting a hidden structure like Gauss, pairing the numbers up, and defining your terms so clearly that you don't accidentally divide by 0 and blow up the logical universe.
And it's about rigorous honesty. You can't just say, well, it looks like a square. You have to definitively prove it's a square. You can't assume the thing you're trying to prove to begin with.
Right. It's a discipline that forces you to slow down and verify your own assumptions.
Yeah.
In a world of total information overload, where people constantly use authority arguments or tell stories where the numbers just don't add up, like the bellhop tip mathematical thinking is a superpower, it's an incredibly precise bullshit detector.
Before we wrap up, I want to leave you with a final thought from Sullivan's book. We talked a lot about the Pythagorean theorem today. If you have a right triangle, then a squared plus b squared equals c squared.
Very true.
But here is the question for you to mull over. Is the reverse actually true? If you have 3 completely random numbers, a, b, and c, and they just happen to satisfy the equation a squared plus b squared equals c squared, does a right triangle necessarily exist with those side lengths? Or is it just a numerical coincidence?
It's a very subtle difference in logic. It's the distance between saying if it's raining, the ground is wet, and if the ground is wet, is it raining?
Exactly. Think about that. Look for the hidden logic in your daily life. Thanks for taking this deep dive with us.
Keep thinking critically.